is the expression 2 times x1 squared plus 12 times x1 times x2 plus 20 times x2 squared always positive? Let's try some inputs. Plug in x1 equals 1 and x2 equals 0 and we get 2. Positive. Plug in x1 equals 1 and x2 equals negative 1 and we get 2 minus 12 plus 20, which is 10, still positive. But guessing values forever won't prove it for every input. There's one algebraic move that settles this question for all inputs at once. And here's the surprise. That move is something you've already done in linear algebra without realizing it. Let's start with a symmetric 2x2 matrix A, with entries A, B on the top row and B, C on the bottom row. A quadratic form is the product x transpose AX. That means a row vector on the left, the matrix in the middle, and a column vector on the right. When you multiply it all out, you get a times x1 squared plus 2b times x1 x2 plus c times x2 squared. Notice there are no linear terms and no constants. This is pure degree 2. The diagonal entries of A become the coefficients of the square terms, and the off-diagonal entry B appears twice, once above and once below the diagonal, so the cross term picks up a factor of 2b. For our example, we choose A with diagonal entries 2 and 20 and off-diagonal entry 6. Plugging in, we get 2x1 squared plus 12x1 x2 plus 20x2 squared. A matrix is called positive definite when the quantity x transpose AX is strictly greater than 0 for every non-zero vector x. Geometrically, this means the surface Z equals x transpose. AX is a bowl that only opens upward, touching 0 only at the origin. Here is the challenge with our example. The cross term 12 times x1 times x2 can actually be negative when x1 and x2 have opposite signs, so positivity isn't obvious from just staring at the expression. We need an algebraic transformation that makes the answer visible. Now let's complete the square. Start with 2x1 squared plus 12x1x2 plus 20x2 squared. First, factor a 2 out of the first two terms, giving 2 times the quantity x1 squared plus 6x1 x2 plus 20x2 squared. Inside the parentheses, we complete the square by adding and subtracting 9x2 squared. That turns x1 squared plus 6x1 x2 into the perfect square x1 plus 3x2, all squared, minus 9x2 squared. Now distribute the 2 across the bracket. We get 2 times x1 plus 3x2 squared minus 18x2 squared plus 20x2 squared. Combine the x2 squared terms, negative 18 plus 20 equals 2. The final form is 2 times x1 plus 3x2 squared plus 2x2 squared. Notice that both coefficients out front are positive 2's. The expression is a sum of two non-negative pieces, so it is always at least 0. And it equals 0 only when both squares vanish, which forces x1 plus 3x2 to be 0 and x2 to be 0. Hence, x1 is also 0. So the form is strictly positive whenever x is non-zero. Positive definite, proven. Watch what happens when C shrinks. Drop the bottom right entry from 20 down to 18. Repeating the same completion of the square now gives 2 times the quantity x1 plus 3x2 squared plus 0 times x2 squared. The second coefficient has vanished. The form is still never negative, but now it hits 0 off the origin. Choose x1 equal to negative 3x2, and the single remaining square dies. This is positive semi-definite, the borderline case. Semi-definite does not mean sometimes negative, it means never negative, but 0 in some non-zero direction. The missing square, not a negative 1, is the signature. Now let's drop C further, all the way down to 7. Running the same completing the square procedure, we get 2 times the quantity x1 plus 3x2 squared minus 11x2 squared. Look at that second coefficient, it's negative. To witness the negativity directly, set x1 equal to negative 3x2. That choice kills the first square, leaving just negative 11x2 squared, which is strictly negative for any non-zero x2. So the form takes on both positive and negative values. We call this indefinite. The negative coefficient is our witness. It points directly at a vector where x transpose ax goes negative. 3 cases, 1 procedure. The signs of the squared term coefficients tell you everything you need to know. All positive means positive definite. 1, 0 means positive semi-definite. Any negative means indefinite. Here's a common trap. Many students think that if every entry of the matrix A is positive, the matrix must be positive definite. That's false. Let me show you a counterexample. Take A with diagonal entries 2 and 7, and off-diagonal entries both equal to 6. Every single entry is positive, but this is exactly the C equals 7 case from before, and we already showed that 1 is indefinite. To see it directly, plug in the vector with x1 equal to negative 3 and x2 equal to 1. We get 2 times 9 plus 12 times negative 3 times 1 plus 7 times 1. That's 18 minus 36 plus 7, which equals negative 11. Negative. So positive entries are not the test for positive definiteness. The sum of squares decomposition is the real test, which raises a natural question. Where did those numbers, the 2 out front, the 3 inside the square, and the minus 11 actually come from? Let's run Gaussian elimination on the matrix A with diagonal entries 2 and 20, and off-diagonal entries both equal to 6. The first pivot is the leading entry of row 1, which is 2. To eliminate the 6 sitting below it, we multiply row 1 by 6 over 2, which equals 3, and subtract that from row 2. So 3 is our multiplier. The new bottom right entry becomes 20 minus 3 times 6, which equals 2. That's our second pivot. So we have 2 pivots, both equal to 2, and 1 multiplier equal to 3. Now look at the sum of squares decomposition. 2 times the quantity x1 plus 3x2 squared plus 2 times x2 squared. Notice the same numbers appear. The pivots, the 2 outside 2's, sit outside the squares. The multiplier, 3, sits inside the square next to x2. Pivots outside, multiplier inside. Completing the square and the Gaussian elimination are really the same procedure, just dressed in different clothes. 2 methods, 1 underlying calculation. When you eliminate, the pivots become the outside coefficients of the squares, and the multipliers become the inside shifts. So the test for positive definiteness collapses to something wonderfully simple. The matrix A is positive definite if and only if all of its pivots are positive. Row reduce the matrix, read off the pivots, check the signs. The bowl shape, the sum of squares, and the elimination steps are 3 views of one and the same structure.